All right, hello and good evening, everyone. Welcome to the Marshall W. Allworth Planetarium. My name is Jessica. I am the director and will be one of your cosmic Mythbusters tonight. We've also got Rachel, one of our students, in the back helping out, and you also met Clayton at the door. So we are here tonight for Mythbusters Astronomy. We're going to take a look at some common myths, misconceptions, and some true things as well, and see, what's true and what's false, and talk more about them. Now, if at any time during the show you need to leave, you're welcome to do so. You'll just exit through the same door you came in. Just, of course, be careful because it does get dark in here. Afterwards, if the clouds hold out, we will have a couple of telescopes set up outside to look at the moon. So just keep your fingers crossed that the clouds stay away for just a little bit longer. Now, the show is meant to be a fun, interactive show, so if you have any questions throughout, feel free to ask. And this is run in kind of a true-false style, so I will be asking for some opinions if you feel brave enough to say them out loud. All right, with that, I'm going to head to the back to my controls, and we will get going. All right. To get us going, our first question of the night, or I guess not question, statement, is it true or false that there is a permanent dark side of the moon? Anyone feel brave? Couple hands. They're true. Here's some false. All right, let's find out. It is in fact false. And I will say, I blame Pink Floyd for this one. But let's talk about it. So here we have our gorgeous moon. This is what we would consider from here on Earth a full moon. It looks exactly like we think it does. It's pretty, it's great. But now if we hop on over to the other side, we do see it's dark. So clearly there is dark sometimes, but is it all the time? Well, we can figure that out because I can just fast forward time and we can watch over the course of the month. Well, it does light up. It is not dark all the time. So, if there isn't a permanent dark side of the moon, if all of the moon does get sunlight at some point, where did this idea of dark side of the moon come from? And I think it has more to do with the use of the word dark to mean unknown. Because while there isn't a dark side, permanent dark side to the moon, there is a side that for a while was unknown. So if we watch the moon here, and just for reference, I did make the Earth and moon a lot bigger so we can easily see them. I did also turn off the nighttime for now, just so we can keep clear of what the moon we're looking at. If you watch these dark markings on the moon, you'll see as the moon orbits the Earth, those dark markings are always facing the Earth. Meaning we always see the same side of the moon. So I think that's where this idea of dark comes from, meaning the other side, the side that we don't see, that for a while was very mysterious and unknown, and until we sent spacecraft out, we had no idea what the other side of the moon looked like because we never see it. But then that begs another question. Why do we only see one side of the moon? And commonly people think that this must mean that the moon isn't rotating. Like we clearly see the Earth rotating here. And I can understand where that idea comes from, but it's not right. So I'm going to put up a little graphic here. We're going to see two systems. one with the moon rotating and one without. Let's look at the right one, the one without the moon rotating. We actually see that if the moon doesn't rotate, we would see the entire moon. So clearly that means it has to be rotating. What's happening is the moon is what we call tidally locked. That means in the time it takes for the moon to make one complete orbit around the Earth, that's the same amount of time it takes for it to complete one rotation. And because that one-to-one tidal lock, it rotates in the same amount of time it takes to orbit, that very slow rotation keeps the exact same side of the moon always facing us. And it's not coincidence that this happens. This is actually an effect of tides and gravity. So this is something that Earth's gravity pulling on the moon slowly caused to happen over billions of years. So now it's to the point where it's tidally locked. And as a fun little addition to this, if I turn the nighttime back on, we can clearly see that while the same side faces us, it's not always lit up. And that's what creates our phases. Our phases are really just what part of the moon facing us is being lit up by the sun. And just to reiterate, as we watch the moon go around and around, you do see the entire moon does get sunlight at some point over the course of the month that it takes to go around the Earth. So no permanent dark side. We do have a far side that's unseen by us here on Earth, and some pretty cool physics going on as well. At least I think so. All right, you ready for our next one? Okay. Here's our next one. True or false? Astronauts in the ISS, the International Space Station, are weightless because there's no gravity in space. I heard a false very quickly. Anyone else? All right. This one is false. You are correct. There is gravity in space. In fact, it's gravity that's causing the space station to orbit the Earth. If that wasn't there, the space station wouldn't be orbiting. Now, instead of explaining this myself, I found a fantastic quick video by Veritasium, fantastic YouTube channel if you're ever interested in sciencey things. And I figured I'd let him explain this one because he does a really great job. So let me get that going.
Have you wondered what it would be like to be an astronaut floating around in the space station? But why are the astronauts floating? I'm here at the Powerhouse Museum in Sydney to find out if anyone knows the answer. But why are they floating? No gravity.
No gravity.
Zero gravity.
There's no gravity.
The stuff that holds us to the planet when we spin doesn't happen up there.
Gravity holds you down, so in space there's nothing there, so it's floating.
There's no gravity in space.
No gravity, there's very little.
But is there really no gravity in space? After all, the moon orbits the Earth due to gravitational attraction. So, where would the space station fit in this picture? Can you give me roughly the scale model of the Earth and the moon? And then we're going to position the space station in there. Is that right like that?
Yeah. Closer. About there.
You ready to see the real distance? What do you reckon? Oh, okay. It's actually about here. Maybe a little further. Now, if the moon is here and the Earth is there, whereabouts would you put the space station? Around here. About halfway? Yeah. Right about here? So that's maybe like a quarter of the distance to the moon. Let me show you the real distance. Are you ready for the real distance? The space station is right about there.
Oh, I get
Okay.
it.
The space station is actually only about 400 kilometers away. So if you're in Sydney, it's a little further than the drive to Canberra. But does it make sense that the Earth exerts a big gravitational force on you, but nothing on the astronauts just a short distance away? You reckon there'd be no gravity there?
It's just much they float, we've seen them.
Well, clearly there's not. They're floating around.
I know they float. And the question is why? Yeah, we're really confused. Well, in truth, the force on the astronauts is almost as much as the force on you. So then, why are they floating while you're stuck here? The answer is the astronauts aren't floating, they're falling. Ah! And not only that, but the space station they're in is falling as well. Ah! So why doesn't the space station come crashing into the Earth? Well, the reason is the space station and astronauts inside have this huge sideways velocity of about 28,000 kilometers per hour. So even though they're falling towards the Earth, they're going so fast that as they fall towards the Earth's surface, it curves away from them. If the Earth didn't put a gravitational force on them, they would fly out into space, surely, right? So it's due to that gravitational pull that they can actually keep orbiting the Earth.
If it was to stop moving, it would be plummeting.
Exactly.
But would they?
They would still feel weightless until you smash into something. So the space station and the astronauts inside are constantly accelerating towards the Earth's core, but they never get any closer. And because they're accelerating at the same rate, the astronauts feel weightless. They have this amazing sensation of floating.
All right, there we go. So I love his explanation of it, but essentially, being in orbit is falling. It's falling and missing the ground. And they just are constantly in a state of falling. In fact, have you ever like missed a step or forgotten there was an extra step, and for a second, as you're like falling that little bit extra distance, you feel like your stomach churn, you feel like a little bit weightless, a little bit less weight. That's what they're feeling all the time. It's pretty cool. And honestly, a big reason why I do not want to go up there, because I do not think I have a strong enough stomach to handle that constant feeling. All right, on to the next one. True or false? We have winter when the Earth is closest to the sun. I hear some true, I hear some false. All right, well, let's see. This one is true. Yeah, we actually do experience winter, at least us in the northern hemisphere. We experience winter when the Earth is closest to the sun. That's because our distance to the sun is not the cause of our seasons. So let's talk about this in parts. We're going to start off with this whole idea of being closer or further from the sun. So if we take a look at Earth's orbit around the sun, it looks nearly perfectly circular. But it's actually not perfectly circular. It is slightly elliptical, which does mean at some times in the year we're a little bit closer, and at some times of the year we're a little bit further away. So this picture is a big exaggeration of this. But you can see the difference between our closest and our furthest from the sun is about 3 million miles. So not a whole lot in the scheme of the 93 some odd average miles we are from the sun, but there is a little bit of a difference there. And we are actually at our closest in January and our furthest in July. So if it's not our distance that's causing the seasons, what is? Well, you can already kind of tell in this picture that the Earth and its axis is slightly tilted. But let's get a better look at that. So just like I did for the Earth And the moon, I am going to scale the Earth up so we see it a little bit better. I am highlighting where the equator is. And you should also be able to see coming out of the poles where Earth's axis is. So I currently have this set up for the Earth on the summer solstice, which is usually around June 21st. And we can see because the Earth is tilted, at this time, the northern hemisphere is tilted towards the sun. I didn't scale the sun up. That's why it still looks really small. But the Earth and the northern hemisphere is tilted towards the sun. What this ends up doing is it makes the sun reach higher in our sky. And that means its light is being concentrated on a smaller area. So you get more heat being delivered to that area of ground, which causes the Earth to heat up. That, coupled with the fact that the sun is out for a longer period of time, leads to the northern hemisphere heating up, and we have our warm weather, we have our winter. Now, 6 months later, when the Earth is on the other side of its orbit, we, the northern hemisphere, are now tilted away from the sun. And we end up with the exact opposite effects. The sun is lower in our sky, which spreads that light out over a larger distance, a larger area, so you don't have as much heat per meter square per area being delivered. And the sun isn't out for very long. All of that leads to less heating, so the northern hemisphere cools down, and we experience winter. Now, of course, since we are tilted and there are two hemispheres, this is why we have opposite seasons in the northern and southern hemisphere, because while we are tilted away getting our cold weather, the southern hemisphere is tilted towards getting warm weather. So they have summer when we have winter, and vice versa. As a last kind of side note, halfway between our two extremes, our two solstices, we have days we call the equinox. We have a spring equinox and a fall equinox. And if I spin us around here, these happen at the times when the Earth is not tilted towards or away. And that means the sun is up for roughly 12 hours, and we get equal amounts of daylight and nighttime, hence equinox, equal night. That's what that means. So rolling right through this on a very related question. Here's our next statement. True or false? It's much easier to balance an egg on its end on the equinox. What do we think? I guess, has anyone heard that before? Yeah? Okay, so we've heard it. What do we think? Do we think it's true or false? It is false. Yeah. So I think where this idea comes from is this orientation. If we're not tilted towards or away, then I think some people think that the sun must be like directly overhead, which means it would pull upward on the egg a little bit more, making it easier to balance. But there's a lot of easy ways to debunk this. First, let's take a look at Duluth on the spring equinox. The sun is not directly overhead. It gets to about 43 degrees above our horizon, not 90 directly overhead. And that's because the Earth's surface is curved. So it's not going to be directly overhead for most of the Earth. The only people on the equinox who will see the sun directly overhead are people who live at the equator. But even besides that, the sun is so far away that even if it was directly overhead, there would be a negligible pull on that egg. And what I think happened when this spread is people tried it. right? They tried to balance an egg on the equinox and got it to work and thought, aha, it must be true. So they shared it. But to be a good scientist and to really test this out, you not only have to test it on the equinox, but you have to test it on other days as well. And they didn't do that. But you'll find that it's just as easy or really just as difficult to balance an egg any day of the year. So yeah, fun little one to tie in with our seasons there. All right, for our next one, we are going to talk about Jupiter. So, true or false? Adding just a small amount of mass to Jupiter would turn it into a star. False? False? I'm hearing lots of falses. Okay. This one is false. Yeah. So again, I think this one starts out in a slight misunderstanding. Jupiter is made up primarily of hydrogen and helium, just like stars are. But there is a lot less to Jupiter. So let's first compare Jupiter to our sun. So Jupiter is about 1/10 the size and several hundreds and I think even thousands times less the mass of our sun. So even adding just a little bit to Jupiter would make it nowhere near what our sun is. Okay, well, there are other types of stars out there. In fact, there are things called red dwarfs, which are small red stars and are smaller than our sun. So let's compare Jupiter to one of those. Now we're going to add in Proxima Centauri, right there. Okay, well now I'm really starting to see where this idea could come from. Proxima Centauri, this small red dwarf star, is really not that much bigger than Jupiter. But while it's not that much bigger in size, it's a lot bigger in mass. We're talking at least 80 times Jupiter's mass is concentrated in that star, in that small little red dwarf star. Now, the reason we see a small size difference, even though we have such a big mass difference, is gases compress, right? As you start piling more on and gravity starts pulling on it, the gases continue to compress themselves. And so you end up being able to add a lot more stuff while not getting that much bigger of an object. So in reality, if we wanted to somehow turn Jupiter into a star, we would need at least 80 Jupiters to smash together. And maybe at that point, the gravity and the temperatures and the pressures at the center could ignite hydrogen fusion. And if that happens, then yes, it could become a star. But it's not just a little bit that you have to add. You have to add quite a bit of mass to get it to that point. All right, we have 2 more topics left, and I think they're both really fun. So on to the penultimate. True or false? Stars do not move. What do we think? I'm hearing a little bit of both. All right, let's find out. This is false. Stars do move. So let's talk about this. Our sun and all of the other stars in our galaxy are moving. We are moving around our galaxy, around the center of our galaxy. And all of the stars that we see in our sky are moving at slightly different speeds. The thing is, these stars are also really far away. So it takes a long time for us to notice. So in our lifetime, you're not going to see any movement. You're not going to notice anything. But with the planetarium, we can go much faster through time than you normally can. So you can kind of watch the date, the year down here. What I'm going to do is I'm going to set this going so that we're moving at 1,000 years each second. Okay? And as we start going, you'll notice we got some movement here, we got some movement here, little bit of movement. We're not seeing a whole lot, but we're still seeing some. So let's make it really obvious. Let's now jump 10,000 years at a time. And once I do that, oh boy, you can see a move. So the patterns we see, the night sky as we see it, all of that is going to change over thousands and thousands of years. As these stars, and I just stopped it again, as these stars all orbit around the center of our galaxy. So yeah, stars do move. It's just not easily perceptible with our short lifetimes. But it is something we already see when we compare the star charts we make today to those that were made thousands of years ago. For some of the fastest moving stars, you can already see a difference in their positions. All right, we ready for our last one? Save the best for last. We're going to talk about black holes. So true or false, black holes suck everything in. All right, here we go. The answer to our last one. It is false. I know, black holes get a really bad rap. Okay, so let's talk. First, let's talk about what a black hole is. So a black hole is an object where you have so much mass concentrated into such a small volume that gravity is at its most extreme. And that gravity is so strong that not even light can escape from it. And hence the black holes, because no light can escape. The thing is, that's not true everywhere. There's a distance that you can get from a black hole where you're safe. But once you pass the point of no return, the event horizon, that's when gravity becomes so strong that you can't escape it. So as long as you stay outside the event horizon, you're fine. For example, if our sun was suddenly replaced by a black hole that was the equivalent of one sun in mass, that event horizon would be about a mile from the black hole. That's it. You'd have to get that close to it to be sucked in. All of the planets that are orbiting would keep orbiting. Nothing would happen to us. We'd freeze because there's no heat. But our orbits would stay fine. We'd just keep orbiting around. So they're not these giant cosmic vacuums that just suck everything up in their path. The only trouble is when you get too close. Which leads to the very last thing for tonight. What does happen when you get too close to a black hole? And I am going to let Neil deGrasse Tyson take over for this last bit.
And now for another installment of What If? You ever wonder what would happen if you fell into a black hole? First, some background. Black holes are regions of space where the gravity is so high that the fabric of space and time is curved back on itself, taking exit doors with it. Light is the fastest stuff in the universe. Not even light can escape. Light can't escape. Neither can you. Which is why we call these things black holes. This boundary within which light cannot escape, we call that the event horizon. All the stuff within the event horizon has collapsed to an infinitesimal point at the center. Ready? Here we go. I'm going to fall to the black hole feet first. As I get closer and closer, the force of gravity grows astronomically, but I can't feel it. Because, like anything else in free fall, I'm just weightless. But I'm starting to feel something else. Something sinister My feet are closer to the black hole, so gravity pulls on them harder than at my head. This difference in force from head to toe is normally tiny, and it goes unnoticed on places like Earth. But in a fall towards a black hole, this stretching force is all you'd notice. If I were made of rubber, then I'd just stretch. But our bodies are made of things like bones and muscles and organs. I would stay whole until the stretching force exceeded the molecular bonds in my body's flesh. At that moment, my body would snap into two segments. That's not even the worst part. Everything of me that ever was gets funneled to the black hole's center. So not only have I been ripped in half, I'm being extruded through the fabric of space and time, like toothpaste through a tube. As I keep falling, the difference in gravity continues to grow, and each of my two body segments snaps into two more segments, and so on, splitting my body into ever-increasing number of parts, all the way down to the atoms themselves, and beyond, leaving an unrecognizable array of particles that just a few moments earlier had been me. We have a word for this cause of death: spaghettification.
That is real. Spaghettification is a real term. It is my absolute favorite thing. And I have to tell you, this is one of the moments where it's like astronomers are either so good at coming up with names, like spaghettification, or really bad, like the Very Large Telescope. But yes, falling into a black hole would not be a good thing. And think about that next time you watch your favorite sci-fi adventure that has people traveling through black holes. Probably not a good way to travel. All right, with that, that brings us to the end of our Mythbusters show. Were there any other questions? Yes.
I always heard that black holes were planets or something that had collapsed on itself and became so dense that it was a black hole. Is that not true though? It wasn't a planet there that just collapsed?
No, it wasn't a planet. Black holes tend to form from massive stars.
Yeah.
So stars that are at least 25 times the mass of our sun. When they die, they can, if they have enough mass, can collapse in on themselves and create a black hole. Yeah.
That's not the only way they're formed.
That is, yeah, there are other ways. If you have like remnants of stars, dead cores of stars like white dwarfs or neutron stars, and they merge and they exceed that limit needed to create a black hole, they can create a black hole. There are also supermassive black holes at the centers of galaxies that we do not know how they formed. That's one of the lingering questions in galaxy evolution and the formation of galaxies, is how do these supermassive black holes form? And that's something that hopefully the James Webb Space Telescope is going to help us answer.
Something with gravity, like that's another one. When they practice and they get in a plane and dive, is that the same principle? Why they float and they have to practice? They can just do it for a couple minutes and the plane dives?
Yeah.
It's the same principle?
It's the same principle because as the plane dives, it's essentially free falling. Yeah, the, what do they call it? The vomit comet? Also not something I ever want to experience. I don't even like regular flying, so yeah. I see another hand. Yes.
I'm having a little trouble with our sun collapsed and became black hole or whatever. But anyway, the planets orbiting whatever star did collapse, and they remained there. To me, if that were the case, if it didn't pull things in, then it never, I mean, it'd quickly go dark. There wouldn't be light to keep pulling in. It's pulling that from someplace. I can't make that work out.
So the light and the gravity are two different things. So anything with mass has gravity. You have gravity. I have gravity. It's just really big things have a lot stronger gravity, which is why the Earth holds us to its surface. But my gravity doesn't pull you towards me because our gravity is really, really, really small compared to what we're feeling from the Earth. So in my example, if the sun was just instantly replaced, so I'm not talking about the sun being turned into and that whole process. If it was just instantly replaced with a black hole, because mass is what determines gravity, if it has the same mass, the gravity the Earth feels wouldn't change. So our orbit wouldn't change. That make more sense? Yeah.
All right, any other questions?
All right, well, I think they've got telescopes set up. We'll go see how things are looking, but we've got a hopefully beautiful moon out there. I will be back here if you have any other questions or just want to come chat. But thank you all so much for coming out. I hope you enjoyed the show.